I'm Ben Johnson. I work a lot in Go and databases, and I'm going to be talking about writing production applications with Go and using this great database called SQLite. Just a quick background on me. I've been writing Go for quite a while now, about 8 years now. I write a lot of open source as well. So BoltDB is one example. It's a key value store. It's used in projects like etcd or Console. I also am writing a project right now, or have a project called Litestream that we'll talk a little bit about later. A lot of my focus right now is getting SQLite really production ready and getting it to deploy out in all kinds of projects. I do a lot of blogging as well, so you can find blogs about Go project structure on Go Beyond. It's a blog I have. And finally, I just really love embedded databases. I think they're awesome. So this talk is going to be very biased, but I hope you follow along with me. So whenever you start a project with Go, you're always kind of the biggest question is, which database do you choose? There's a myriad of options out there. There's traditional options like Postgres, MySQL, SQL Server, Oracle, those kind of things. But you have a lot of new ones as well. You have all kinds of options from Amazon, so RDS, Aurora. You have PlanetScale out now. There's just tons of database options. What do you choose? Now, a lot of these databases, they have benefits and they have trade-offs as well. A lot of these are familiar, so a lot of you have already used maybe Postgres already. A lot of these databases have been around for 40 years, some of them, so they're quite robust, and they just have tons of features in them. They just collect features over the years. Now, you get some trade-offs with all of this as well. One thing is expense. So if you have a separate server to run a database on, that's an extra server to run. If you're doing cloud databases, they get charged per operation. And a lot of these databases get bloated over time with all these features. And then finally, the last trade-off, I think is one of the most important, is high latency. So connecting to another process or connecting to another server can really take up a lot of the time of your processing and your query speed. Now, in addition to the client server and cloud options, one I don't think most people consider would be SQLite. And it's, for a long time it was kind of considered a toy database or a test database, but really it's so much more. Like it's an in-process database, it's an embedded database, which means it actually gets compiled into your source code and deployed with your application everywhere it goes. It's super stable, super safe. This runs on all kinds of devices. So your cell phone has it installed on it. It's installed on airplanes. It's installed in all kinds of places. And it's been around for about 20 years now. First released back in 2000. Now, SQLite provides a lot of great guarantees like any other database. So ACID compliance. We're talking about atomicity, consistency, isolation, and durability. That means that whenever you write transactional data, it gets saved safely, and you can trust it. In addition, it has a lot of SQL support you might not consider. It has things like windowing functions. It has things like common table expressions, recursive queries, subqueries. Most of the things you expect from a SQL database are in there. And finally, it has non-SQL support. That's really great. You have full-text search, so things like Elasticsearch you don't always need when you have the built-in full-text search within SQLite. It also has JSON support. So if for some reason you are storing JSON in your database, you can query it. I don't recommend that generally, though. So as far as when you should really consider SQLite, historically, it was used in embedded software. That was kind of its biggest use case. It gets used on like edge databases, things like that, small resource-constrained servers. And that was kind of its purpose for a long time. Now, there's been a lot of improvements over those last 20 years, specifically in concurrency. So it does really make sense as like a multi-process or multi-threaded database. So because of that, it's really useful for read-heavy workloads. You might consider it for something that, like an e-commerce website, for example, where you have someone going to a lot of pages. Those are all read queries. And then every once in a while, maybe adding to cart or checking out. Those would be write queries. It's good for small to moderate request load, things like tens of requests or hundreds of requests per second, which probably covers most applications out there. And really SQLite has kind of grown so much over the years that it can kind of be considered a general purpose database for a lot of applications. Obviously no tool is used for everything, and they all have their specialties, but it's I consider it a good default to start with. I think historically I always consider Postgres as my option, and then try to think about why would I use something else? These days, I really look at SQLite as kind of my default database, and then consider why I would use something else. So this talk's going to be split up into 3 different parts. We're going to talk about kind of the development side, the testing side, and then finally we're going to get into kind of the production database side and what that really looks like from a durability and a performance standpoint. Now, when you connect to SQLite, you have basically 4 options out there. There's probably some extras, but these are probably the most popular. The most common library out there is going to be the matn library, Go SQLite 3, and honestly, this should just be your default. It's used in all kinds of places. It's been around for years, stable, and great. I have no complaints about it. This is the one I typically use. There's also a project going on from Modern C, where they've actually transpiled, like mechanically transpiled, all the code from SQLite into Go, so you can actually compile it as a Go library. Then you avoid the CGO overhead and any issues around cross-compiling. Next, we have the low-level SQLite database. If you want to avoid the database/SQL library, you can use this one by David Crawshaw. And then finally, Tailscale is actually working on an implementation right now that has some improved benefits with concurrency over the matn library. It's a work in progress, but definitely check it out. They're doing some good work. So when you connect to SQLite, this is actually going to be pretty brief. You use it like any other driver for database SQL libraries. So you import it with a underscore before, because you're not referencing the actual name of the library. And then in the SQL.open, you are going to just pass in the driver name, which is SQLite 3. And then for the data source name, instead of a URL or a network path, you're going to actually pass in the path to the file on disk. And then after that, from then on, that database connection, really you can just treat it like any other database connection. Now, I generally consider SQLite pretty configuration-free. There are a couple exceptions here that are worth noting, and we'll kind of go over those. But once you get these set, there are some knobs you can tune if you really want to later on, but generally it just pretty much works. Now the first one here is probably the most important, I find. It's called the journal mode. And journaling in databases is how you safely write a transaction to disk. And what happens here is the default mode, the original mode, was called a rollback journal. And you'd write whenever you wrote disk or data to your database, it would go into, you take the old data, put it into a rollback journal, and then you'd write the new data to your database, and then you delete the rollback journal. There's a new mode in here since 2013 called the wall mode. This stands for write ahead log, and what this means is that you're going to write all your new data to the separate file instead of your database, and you get a lot of concurrency benefits with this. You actually get point-in-time snapshots for every transaction, as well as you're able to write and read at the same time. There is a limitation on SQLite where you only have one writer at a time, but you can have as many read transactions as you want. Next, this is kind of an odd one if you're coming from other databases. It's called the busy timeout. The busy timeout sets how long a write transaction will wait to start. Now, again, SQLite only supports a single writer, so that means if one's active and another write transaction starts, by default it'll just fail immediately. That's not usually what you want. So instead, we'll set this to the number of milliseconds we want to wait. I usually use 5 seconds. Sometimes you can use 30 as long as it's more than 0. That's kind of the biggest thing. And we're going to use this format here with a pragma, which is essentially a way to set settings on SQLite. So we're going to do pragma busy timeout equals 5,000 for 5 seconds. Final option that's really important is foreign keys. And a lot of these are for historical reasons as to why you have to set these things or why they weren't enabled originally. Foreign keys are not enforced by default, which is pretty surprising for most people. SQLite started off on very resource-constrained systems, so you didn't want to necessarily use all that processing power for foreign key constraint checking. So what we can do here is we just set pragma foreign keys equals on, and it'll enable enforcement for your foreign keys. So those are the main settings you want to set with SQLite, I find. Another side of SQLite you really need to kind of get used to is the type system. It's a little weird, but it's not as bad as a lot of people consider it. The first thing to note is that the type system is pretty small. You have integer, you have real, which is the floating point numbers. You have text for readable text and blob for binary data. But this actually pairs well with the Go type system. We have integers, we have floating point numbers, we have strings, and we have byte slices. And finally, we have null, which is kind of no data at all. Now, the really weird part about the type system in SQLite that people kind of get thrown off by is that a column isn't necessarily associated with the type, it doesn't have like a strict type. Every value you insert into the system has its own type. And type definitions on tables and their columns are basically ignored by default. So here down below, you can see we have a create table with an X and integer and a Y text. But SQLite largely ignores those types, and you can insert text into X or you can insert integers into Y, and it'll just let you do it, which personally seems insane to me, but that's how they set it up. Luckily, actually, just only 2 weeks ago, they added support for strict mode, which actually enforces the column constraints, and a couple other options too. So I don't have time to get into this presentation, but it's something to look into. The last thing you kind of caveat you got to worry about when you're developing is that SQLite kind of has some types I really wish it did have. It doesn't have. These two are timestamp and decimal types. For timestamps, while there's no type actually available within the type system, it does have some datetime functions, and these functions will work with 3 different types of dates. The first one is ISO 8601. In Go, this is known as RFC3339. This is a string format where it's nice because it's actually lexicographically sortable naturally, so you can just sort them and use them in indexes, and it works as you expect. The other option, you can use Unix epoch, which is the number of seconds since 1970. This will give you an integer, which is, shrinks down the amount of space you're using for each column. And then finally, there's something called the Julian date. I would generally advise against this one because most people have no idea what it is. It's the number of days since about 4,700 BC. Again, it's pretty obscure, but there are some applications for it. But I would generally avoid that one. Now, the development side, once you kind of get it connected, get it up and running, it's really a pretty good pleasure to use once you get around those caveats in the type system. Another piece of it that's super nice with SQLite is the testing is just super fast. Now, the biggest thing with the type system, like if you come from an ORM that allows you to run against multiple databases, a lot of people will actually run their tests in SQLite because it is so fast. Again, it's built into your application and compiled in there. But the bigger thing is that it has native support for memory-backed databases. This means, you're not going to have any slow disk access. You're not going to have fsync calls. Everything actually lives on the heap. We can do this by setting the data source name, or the DSN, to :memory:, and then everything will just be in memory from that point on. And again, you just use that database like any other database, except now it's screaming fast. We can do some benchmarking here with SQLite. Again, this is very much loaded in favor of SQLite, but we're comparing this here, Go SQLite in memory versus kind of a standard Postgres setup that people use for testing. Both are the default configurations, and just kind of understanding how the performance changes. So with Postgres, certain operations you need to do that you don't need to do on an in-memory database. So if you need to drop if exists, you don't need to do that for in-memory databases because you wipe it out every time you close it. So for Postgres, we're talking 5.5 milliseconds. For create table, it's 3 times as long as the in-memory version, and some of that is just the connection time. And then when you get down to inserts and selects, it's again screaming fast, where we have 25 microseconds for selects and inserts versus around half a second for inserts and selects on Postgres. So again, it's not quite apples to apples, but it's a good idea to understand really the scale of difference between the two. Another thing you can do is parallelize your tests for SQLite. Again, because it is in memory, there's really a shared nothing approach between the different databases for each of your tests. You can use t.parallel to run these tests in parallel. There's some options on Go tests where you can flag the level of parallelization. The one caveat here is that Go SQLite 3 has a global lock on its connection. So it'll actually slow down parallel tests. If you want to get better performance for these parallel tests, you need to use a tailscale implementation. Here's a quick benchmark here to kind of illustrate the point. So with SQLite 3 and tailscale, they both run to just under a second and a half. And here we're running about 10,000 small tests. Each test opens a database, creates a table, does an insert select, some very basic testing, and then closes down. We can run that about 10,000 times, again, in memory. But as we scale this out over more cores, for SQLite, it actually ramps up over time to 3 seconds and gets slower, whereas with tailscale, you can see that it actually speeds up quite significantly. So on the development side, we've really seen where it can be pretty easy to get up and running. On the testing side, we find that it's screaming fast and we can just constantly test and get feedback and what we need. But then the thing that people generally worry about is production experience. And that kind of factors into two different ways. We have the durability side and the performance side. Now, before we get into too much on the durability side, on SQLite specifically, this is kind of a quick aside about durability in general. I feel like over the last 10 to 20 years, we've had a lot of conversations around availability, where people had expectations of 100% uptime, and that's not realistic, really. You're looking at 99%, 99.9% uptime, and there's cost associated with trying to get higher and higher uptime. So it's really a trade-off of how much money you want to spend and the complexity around that system and what level of uptime you're expecting. However, on the data durability side, we really don't have that same conversation. And before we talk anymore, it's just important to note that there really is no such thing as 100% durable data. You can make as many copies as you want of your data, but you can always lose them all. So, sad but true. Now, there's kind of a spectrum of durability when we're talking about hard drives and systems. So, when people think about running SQLite on an application, sometimes they just think it's like a server in your closet that has a hard drive, and that's not very durable. I mean, Backblaze puts out an annual report where they find, they check all their hard drives and see how often they fail, and they find that about 1 in 100 fail annually. So that's a 99% durability. 1 in 100 chance isn't too bad for a lot of things, but losing all your data, you probably want something a little more safe. Now, you can upgrade, look at something like cloud servers, where they tend to have a bit higher durability with their hard drives. They can be rated. They have other options around that too. EBS, most of its volume, so this is Amazon's elastic block storage. Most of their drive types have 3 nines of durability. This means that every year they lose about 1 in 1,000 hard drives. That's better than what we had with one hard drive, but still, it's not amazing when you're considering losing all your data. You can look at something higher, like IO2 on EBS. This has 5 nines of data durability. That means you have 1 in 100,000 drives fail annually. This is getting to something that's much more comfortable. You probably have a bigger chance of dropping the database or deleting a table than 1 in 100,000. So, it's something you can get more comfortable around in data durability terms. Finally, we have S3. This is kind of, on the far end of durability. It has 11 nines, which is crazy. That means you lose like 1 in a gajillion objects every year. So generally, when you put something in S3, you kind of consider it safe to be there. So when we're talking about data durability beyond just a single disk, we start talking about 1 or more servers. So obviously, single server is going to be your fastest, cheapest option, but it's less durable. You have options for doing a primary replica setup, where we stream changes from a primary down to a replica. This is obviously more complex. You have double the number of servers, so there's additional cost. And finally, it's more durable. You have 2 servers instead of 1. There's also more complex situations you can get into. Distributed consensus, for example. You can have a cluster of servers that need to confirm writes before you let them continue. This is really complex, though. If you've ever run, say, etcd, you can kind of understand that there's a lot of complexity and performance you're trading off with using this. But on the other hand, it's really quite durable. You can lose multiple nodes, possibly, and still have your data. So I'll end this kind of aside, this little rant here, with a quick story. The idea here is that no data loss is good, but not all data loss is catastrophic. I'm not trying to throw anyone under the bus here. I think GitLab did a great job documenting an incident they had 4 years ago. So in 2017, they lost about 6 hours of data, which sounds, that's rough. No one's going to have a good day with that. It's unfortunate, but it happens sometimes. They had a primary Postgres replica set up, so streaming data from one primary to a replica. However, the replica just stopped getting updates for some reason. They were trying to figure it out. And during this, while they were trying to figure it out, the operator accidentally deleted the data on the primary when they deleted it on the replica, and they lost 6 hours. So terrible, but GitLab's still around. They haven't fizzled out. In fact, they actually IPO'd this year for $16 billion. So again, this is really a trade-off. No data loss is good, but it's not necessarily catastrophic. So I'm not encouraging data loss by any means, but I think it's something to consider how much your data costs and what you're willing to trade off for it in terms of durability and performance and cost. So with that all said, let's talk about data durability in SQLite specifically. So your first option you should probably consider is just honestly regular backups. If you're talking about running something like IO2 on EBS, you're already getting, tons of durability with that in the first place. And then if you're regularly backing up, then you really have a fallback plan anyway after that, if it fails. So regular backups, the pros here is it's super fast, super cheap, and it's really hard to mess up. It's not a lot of configuration. The main trade-offs here is that you start to get a bigger data loss window. So a data loss window is when you just have data that hasn't been backed up and you lose your primary data set. Anytime in between the last backup and your current data set is your data loss window. Now, you can set up a regular hourly backup or daily backup to, say, S3. And again, SQLite is just a file, so it's really simple to work with. We can back it up, we can compress it, shove it up on S3, and don't worry about it, which is nice. We can use a time-based file naming scheme here. So if you want to name it after the current hour, you can just have it replace the current or the previous snapshot from yesterday, and just have a rolling 24-hour backup, which honestly works great for a lot of applications. The other thing too is B-tree databases, which is most SQL databases. They compress really well. There's usually a lot of extra space in there so that they don't shift around records when they update and insert all the time. And it means that if you have, say a gigabyte database, it can compress down to, a couple hundred meg, and it's not as painful. Also, something else to note with S3 that's interesting is that they make it so it's very cheap to get data into S3, but very expensive to pull it out of. So it works great as a backup solution. You don't do a lot of operations where you're restoring constantly, but those operations pushing it up can be quite cheap. So SQLite has a command line, SQLite 3, and here you can see that SQLite 3 will pass in the name of the database, so it's mydb, and then we pass in the full command here in the double quotes, which is going to be .backup, and then the name of the file we want to back up to. So again, back it up to another file, compress it, push it up on S3, and generally actually works pretty well for a lot of applications. Now, if you can't handle that data loss window of an hour, that can be pretty long for a lot of people, even if you have, again, say 5 nines of durability on IO2. You can look into other options. So this is Litestream. This is a tool that I created. So obviously I think it's the best, but every tool has its situation where it works well in. So the idea with Litestream is that because S3 is super cheap to back up to, is that we can actually continuously back up to Litestream, which is really nice. To S3. So what Litestream will do is it'll snapshot your data at the current point in time, and usually once a day. And then whenever you make changes to your database, it'll read those off that write-ahead log that we talked about earlier. And then it'll compress those, push them up to S3. And if you ever need to recover your database, it can pull down that snapshot, replay all the pages from the wall after that, and you'll have the exact same byte-for-byte database afterward. This works too if you have catastrophic failure. you can set it up to automatically restart and reload and go with that. So again, a bit more complex than your regular backups, but it's a pretty nice option. One user of this, Michael Lynch, he's written a blog post on this where he's looked at moving from different cloud services over to Litestream, and he found that he only spends about 3 cents a month on these the S3 backups. So he finds it as a great, super cheap option. So something to keep in mind. If you do download it, Litestream actually runs as a separate process. SQLite supports multiple processes connecting at the same time, and your actual application has no knowledge of Litestream. It's really like an ops consideration. So here we have Litestream command. There's a subcommand called replicate, and we'll pass in the path to the database, which again is just a file, and then we'll pass in the S3 bucket. Here's just kind of a visualization of Litestream. So we have our database on our application server. Whenever it has changes, it tacks those onto the wall, and then Litestream is pushing up snapshots and continuously pushing up new wall pages as soon as they happen. So this is, again, a good option for reducing that window of data loss, but again, at a trade-off of a little more complexity. Finally, on the durability side, the most extreme example, once you get into data durability, is clustered SQLite, which is a bit of an oxymoron, it kind of seems, but it works for some people. So the pros to this is that it's super durable. I mean, you're going to run a cluster of servers, so the cons here are obviously that it's going to be more expensive. 3 servers or 5 servers is going to be more expensive than 1, and it's significantly more complex. If you've ever run etcd before and tried to manage that, it can be sometimes a bit of a headache. So keep that in mind. And these kind of get split out into a few different types. We have Raft-based. So Raft is a distributed consensus protocol. etcd uses Raft, for example. But SQLite was written by Philip O'Toole, and that's a great option. He's done a great job with that. Canonical also wrote their own implementation of a distributed SQLite called DQLite. And then we have, on a primary replica setup, where we stream from a primary server to a separate replica server, we have something called LiteReplica. This one, I haven't used this personally. It does have a GPL license, so watch out for that if that's a consideration you need. But they do have a commercial license you can check out too. And then finally, there's kind of a crazy project from Expensify called Bedrock. I haven't personally used this one. It's blockchain based, and I have no idea how they do it, but it sounds very complex. Apparently it works for them, so kudos to them, but I have not used it personally. So, on the performance side, we got durability. And if you're comfortable with the durability story, then performance is kind of the next thing you really need to consider when you're talking about performance. Production. Now, performance between SQLite databases is always hard to kind of quantify. You always see synthetic benchmarks out there where one database is X amount faster or X percentage slower, but really you kind of have to test it with your own workload to know what is actually going to happen in the real world, because they're all, again, synthetic benchmarks. Now, the caveat here is that most SQL databases in general are B-tree based. That means they have the same underlying data structure. And because of that, a lot of the performance profile is generally going to be fairly similar. Some are going to have a bit better performance, some are going to have a bit less performance. It's really hard to say for each situation. One might be better than another. However, the one consistent thing is that network latency can be a huge component of performance, and this is really where SQLite shines, because it basically skips over the network piece entirely, because it lives right in your application. So doing some benchmarks here against SQLite versus Postgres, we're doing point queries in this instance here. So it's running about 10,000 point queries on a fairly large database, and we're calculating the time it takes on average for each query. So for SQLite, we see it's way down there at only about 18 microseconds, which is screaming fast. And then, once we start going out of process to another process over some kind of network connection, even on the same box, so Postgres running on the same box, still takes 10 times as long just to get that one point query. Again, this is, connection overhead, this is serialization. There's all kinds of, overhead here that you need to consider. You just don't have a SQLite. Again, it's It's a lightweight database, but again, has some features too. Once we move out of the same server into the same availability zone here, we see that it jumps up, it basically doubles. This is all run in AWS, but we see that it goes up to 300 microseconds. Again, not a ton of time, but if you're running hundreds of these queries or even tens of these queries, that adds up to real numbers. And then finally, running it within the same region, we see it gets 3 times as slow. We're now up to almost a whole millisecond at 900 microseconds. So going down from SQLite at 18 microseconds to same region at 900 microseconds is a huge jump. Now, that's how most people set up their applications when they run their own database server. If you start running against a cloud server, that's a whole different story. It might not even be in the same region as you, so you need to really consider latency at that point. So once we add in cross-region latency, we really start seeing big numbers. This is adding in US East 1, so Virginia, to US East 2, Ohio, which is not very far away, but it still takes about 11 milliseconds. You can't even see SQLite at this point on the graph. It's so tiny. But it's something to really consider. This network latency is going to be a big part of your performance. Now, you might consider that queries can run in parallel, and that works in some situations for sure. But we see when we do parallelize them, we get better performance generally, especially as we have more network overhead. But we really don't get anywhere close to that latency of SQLite because, again, it's in process and it's so close to your data. Now, a lot of times you can scale up a single database on a single server quite large. We have AWS where it can scale out to 96 cores or some ungodly amount of RAM, which is great. Our machines keep getting faster every day. If you ever do reach your maximum of what you can store on a single server and process on a single server, it's time to start thinking about moving horizontally. And horizontal scaling in SQLite is not an often talked about topic because it's kind of seems antithetical since it is an in-process database. However, the benefit here with SQLite is that it's so flexible. It really is just a file. That's all it is. So we can do some pretty interesting things that you might have a harder time doing in other databases. So, for example, if you wanted to isolate your tenants, put a single tenant per database, which can improve your security. They're all just individual files. So we can move them around. We could put them onto a cluster of servers and then distribute those tenants based on like a consistent hashing scheme. This talk, we don't have time to go into consistent hashing schemes, but it's something to consider if you actually do want to fan out your tenants and their data over a network or over a cluster. So again, options out there if you really do need to scale to those bigger data sets. Now, as much as I love embedded databases and SQLite, there's always times when you just shouldn't use a tool. So, I want to, get into that. It's not all sunshine and roses out there. There are considerations here as well. I would say the biggest time when you don't want to use SQLite by far is if you have a working system. Please do not rip out your database and put in SQLite. Your colleagues will hate you. You'll never find happiness in doing that. So definitely avoid that with a working system. A good way to do it is to start off small, have a smaller application, get going with that. And if you really like it, there's always some operational pieces you need to learn around any database. So it's good to get comfortable with that at a smaller scale for sure. Another piece you want to kind of avoid, if you have long-running transactions in your database, usually you don't want those in any database really. With SQLite, it's really a requirement though, because it has that restriction of a single writer. Other databases get around it with some optimistic locking schemes, which can work to some degree. Generally, you want to avoid long-running transactions. Another time to really avoid it is if you have like a truly ephemeral serverless environment. If you don't have a disk or if your disk suddenly disappears when your service is done running, it's definitely time to, you're going to lose all your data. So that doesn't work great. There are some options out there. Services like fly.io, they kind of work similar to Heroku. So you have kind of those kind of dynos or kind of serverless environment, that kind of feel, we can push up to basically a Git repo and deploy. You can do that, but they actually provide persistent disks as well, which really helps a lot. So that's something to consider. So just to kind of wrap up here a little bit, SQLite's great, in a lot of different ways. It's kind of a different paradigm from what you're probably used to with a client-server database or a cloud database, for example. Going back on the development side, it's great because there's just no dependencies at all. You import a library and you're done, basically. There's not really any configuration. You just get up and running. You don't have to worry about users or grants or privileges. It just kind of works. There's not much configuration. We have kind of those 3 pragmas that we set, the journal mode, foreign keys, that kind of thing. So make sure you set those. Those are important. And then, again, the type system, it's kind of weird, a little esoteric, but it actually works pretty well against Go's type system and, enforcing your types at the application layer. And then as far as types go, timestamps and decimals, those are always going to be tricky. But, generally, I would say that RFC 339 timestamps work pretty well. On the testing side, the in-memory support is fantastic. You get your tests running super fast. You can just constantly run them whenever you make code changes instead of waiting seconds or minutes. You get your feedback in, sub-second, even for hundreds of tests. There is parallelization you can use, but again, there's a caveat with that. The Go SQLite 3 library doesn't work as well with parallelization, and you really need to evaluate kind of the tail scale implementation, even though it's it's still a work in progress. On the production side, once you actually do put it out there, there's a couple different options. Again, you have your regular backups. Again, some people may scoff at this, but it's really a great option, especially once you have very high durability drives anyway. You have a known data loss window, but it still works, great, and you put yourself at pretty low risk of data loss in general. If that doesn't work for you, though, options like Litestream, where you can stream your backups up to S3, also work pretty well. Again, you're going to trade off a bit of complexity for that, so just kind of know that going in. And then finally, we have clustered SQLite, which is kind of on the extreme, where we're using something like Raft to replicate, either through RQLite or DQLite. We have Lite Replica, which is a primary replica setup, or there's Bedrock, which is the blockchain-based one. Although if you're getting into clustered SQLite, again, there's not as much of a difference of just using a regular client-server database at that point, so that's something to consider too. On the performance side, single node performance is just screaming fast. Like, you can't beat it. Once you remove that network latency and your serialization overhead, you can really do so much and bring your request times down significantly. And a lot of times you just don't have to worry about things like N+1 queries, and there's just a whole class of performance problems you generally don't have to worry about with SQLite. And then you can scale it up. There's pretty large nodes out there, either on AWS or whatever service you use. And you can also scale it horizontally with some creative ways. Again, SQLite is just a file, so it's super flexible. So really, in conclusion, I hope you give SQLite a try. I love the database. It's not great for everything. Maybe you'll hate it. Maybe you'll love it. But I think it's worth a shot. And yeah, I really like it a lot. So thank you for listening to my talk. Really appreciate it. You can reach me either by email, or you can find me on Twitter as Ben B. Johnson, or pretty much anywhere on the internet as Ben B. Johnson. And yeah, thank you very much.